Welcome back. This video is going to be a brief walk through the use of kernel density estimation to look at sample data that corresponds to the online meeting held on August 25th, 2016 for the Ghana FETLP GIS training. For this workshop, you'll require the Texas data from the Ghana _ KDE folder in my directory. These data are available as a zip file in the e-learning Canvas site under the Files tab. If you're not familiar with how to navigate to that, please see the previous video posted to the group describing how to use Canvas. The first thing I'm going to do for this laboratory demonstration is unzip this Texas data zip file. And you'll see that when I've done that, I'll have two shape files. If we go into QGIS, I'm going to navigate to the local directory where I'm storing those data. And if I simply double-click or drag from the browser panel into the layers panel, I can see the two data sets that I'm going to require to perform kernel density estimation. The first is a ranch boundary. This will ultimately be used to clip the outer extent of any analysis that we perform. It's also what we refer to as a mask. That will be the spatial extent of our final product. And then I have something called the traps _ CPUE. This is a point file. And if we open the attribute table, so I've right-clicked and selected attribute table from the file name in the layers panel. And you can see here that I have a total of 42 features. That's traps number 1 through trap 42. And I have a catch per unit effort, which is the number of biting flies captured per decimal hour that the trap was run. If you'll recall from the lecture given together, looking at slide 13 or PDF page 13 of the PDF file you have, at each of those sites that we just looked at in QGIS, we ran a fly trap for 24 hours, collecting tabanid flies, biting flies, that we think are associated with anthrax transmission in the state of Texas. So that's what these represent, the total number of those biting flies caught per sampling unit time. So the higher that value, the more flies collected there. And the reason we divide it by the sampling time is so that if two traps were run for unequal periods of time, you could still compare them relative to each other by normalizing by that amount of effort. This is what we refer to as the catch per unit effort. Now, our ultimate goal with a kernel density estimation is to produce a continuous surface. And by a continuous surface, meaning we want to fill in the entire shape of this study area with an estimate of the density of biting flies per unit area. And we want to do that with a tool called the Heatmap tool, or the kernel density estimation. In QGIS, to perform kernel density, we use the Heatmap tool. You can see that we have a couple of packages that we need to load. I don't have the Heatmap tool loaded. And we're going to need some vector tools as well. So the first thing we're going to do is go here to Plugins. So I'm going to the drop-down menu, Manage and Install Plugins. And then I'm going to search for Heatmap. I'm going to install the plugin. And it says here that I have now the Heatmap plugin to be able to perform the analysis. So we'll need that in a few minutes. So the first tool we're going to need is that. Now, recall that when we're performing kernel density analysis, we have to set a series of parameters. The first parameter that we discussed at length is something called the standard distance. That's the measure of dispersion, the spatial dispersion of these points around the spatial mean. So we looked at those the other day in slide 9. So the spatial standard distance is a measure of the overall dispersion of points around the mean center. We need that calculation to perform our second parameter test, which is, or parameter setting, which is the optimum bandwidth. A moment ago I opened the attribute table and determined that I had 42 sites. That becomes my N, or my number of sampling units. And the standard distance we can go and calculate together. To calculate the standard distance and the mean center, we need to go into the toolbox, go into SAGA, or you can type SAGA. And when you do that, the Spatial Point Pattern Analysis toolbar will be here in the SAGA processing tools. When we launch that, we'll get a dialog box where we can populate the parameters to calculate each the mean center and the standard distance. To calculate the mean center and standard distance, we have to have a point data set. It's going to be my TRAPS CPUE that we added earlier. Then we need to save the files that we're interested in as outputs, which in this case are going to be shape files. I'm going to navigate to the folder I'm working from. I'm going to create a new folder here called shape files. And then inside of that, I'm going to call this TRAPS mean. Likewise, I'm going to save in the same folder TRAPS stand_dist, TRAPS standard distance. And I'm going to turn off the bounding box. The bounding box, as a reminder from lecture the other day, is going to be a single file that would be a rectangle that reaches the furthest extent east, north, south, and west. So it would create a rectangle of that shape and size, which we don't need for this analysis. I'm going to run this, and when I'm done, I'll have each a mean center. That's the geographic, that's the average UTM easting and northing for this data set. These are in UTM coordinates. It'd be the equivalent of the mean latitude and longitude. So the green dot here is the mean center of all the orange dots. The more important piece of information we need for this experiment is to open the attribute table and calculate or record the standard distance, which you can see from this is 4151.68 meters. Please note that my coordinate system is in meters because I'm working in UTMs. All of the calculations that you perform for populating the hopt, your map units will be the unit of measurement. So you need to make sure that all of your units are the same. So you don't want to be working partially in UTMs and partially in degrees of latitude and longitude. So for this experiment, everything is in UTMs. And in fact, there's a warning for that, or a notice for that, right here in the ranch boundary name, the study area name, indicating that it's in UTM zone 83 14 north. Okay, so I have my standard distance and my sample size. Notice this 42 corresponds to the number of points. If we were to open the attribute table here at the top, 42 features. So now we have the information to populate hopt. We have a sample size in, and we have our standard distance. Now we're going to go over to Calc, LibreOffice Calc. This would be the equivalent of Microsoft Excel if you're using that. And we're going to populate this table. Species is just what we're working with, so this is going to be traps. Sample size is going to be 42. And the standard distance is going to be 4151.68. Remember, that's the information we just looked up together from here in the attribute table. And I've rounded to 0.68. Now we can populate the equation required for the calculation. Okay, so we're going to do an open paren and a second open paren, 2 divided by open paren 3 times the sample size. I'm going to close that set of parentheses. And I'm going to do the caret key. That's Shift 6. Open paren, 1 divided by 4, close paren. And it's indicating here I have an extra parenthetical note. We're going to multiply that times the standard distance. So this equation here is the equivalent of the hopt calculation presented here in slide 10 of the presentation. Oops. I'm going to add one extra set of parentheses there. There we go. So, to just quickly walk through this again, it's open paren, 2 divided by open paren 3 times cell B2, close paren. There's a set of parentheses there. There's a set of parentheses for 2 divided by that value. And then all of that's in a set of parentheses with 1 divided by 4 times the last value, standard distance. If we bring these up on screen together, then we can see we have 2 divided by 3. 3 is multiplied by n. 3 is multiplied by n. 2 divided by 3, that's in its own set of parentheses. That whole output is multiplied or raised to the 1/4 power. That's the equivalent of taking the square root times the standard distance, which in our case is 1,473.63 meters. If you notice a moment ago when I was missing that set of parentheses around the 2 divided by 3n, the value was larger because it did the order of operations incorrectly. Okay, 1473.63. Now we have all the information required to populate our heat map. So I want to run the kernel density analysis on the traps. I need to name my output. So we go to the directory I'm working from. I'm going to create a new folder here called rasters. Remember that from the lecture, creating a continuous surface means going from our discrete points as a vector file to a continuous surface in a raster file. So I've created a new folder called rasters. I'm calling it traps KDE version 1, just indicating that this is the first time I've performed this. I'm going to output it as a GeoTIFF. That's the default raster file for QGIS and very functional for what we need to do. I'm going to set my radius. Remember that the radius is the equivalent of the kernel in a fixed kernel density analysis. And that's going to be set to 1473.63. In layer units, remember those are in meters. I'm going to turn on the Advanced tab. And for this experiment, I'm going to set this to 100 by 100 meters. And you'll see it had actually done that automatically. Because it's a raster file, they're going to be equidistant sides or a square. The other thing I need to do is grab the weight field. Remember, we discussed at the beginning when we reviewed this shapefile that what we're actually interested in is how many biting flies were collected across the landscape. That's stored in the CPUE attribute inside of the traps file. You want to use this weight field in this analysis, otherwise you'd be performing a kernel density analysis asking where is the greatest concentration of fly traps. In this case, we're weighting it by the number of flies and we're asking where is the greatest concentration of biting flies coming from that attribute in the table. This is very important for you to keep in mind when you're performing your own analysis. In this example, where we had just individual carcasses that had died of anthrax, like we discussed on the go-to lecture, each individual dot here represents one dead animal or one wildlife carcass. That's true for each of the buffaloes, zebras, and elephants. In this case, I would run an unweighted kernel density analysis because every individual point is equal. In the case of this example that we're doing together, those are not equal because some trap sites had far more flies than others. So this is an example where you would use the weight field to perform your analysis. Okay, so I've gone to my point file. I've named a raster file so I can make the conversion in this process from a discrete point surface to a continuous raster surface. It's going to be a GeoTIFF, a standard geographically informed raster file. I've set my radius, which is equal to my hopt. To calculate that, recall we had to have our sample size and we had to have the standard distance, which we performed moments ago, and now we're ready to perform the kernel density estimation. And so we can see here that we performed a kernel density estimation. And remember from the lecture that our goal here is to identify where on the landscape is there a greater concentration, or is there a greater concentration than elsewhere. And here we have pretty clearly high values. Notice that from dark to light, or from black to white in this default setting, the wider the areas, the higher the intensity or the greater the concentration of flies. Notice also, though, that our fly distribution, or our trap distribution was limited to this study area. So we're also going to clip our raster output to this study area. And to do that, we're going to do what's called an extraction. We're going to extract this file from this file, or we're going to cookie cut the raster file using the ranch boundary. To do that, we're going to go under Raster, Extraction, and Clipper. Raster, Extraction, and Clipper. Our input file is going to be default. It's going to grab that traps raster file. Notice here it tells us specifically that it's a raster file. And then our output file we have to name. So I'm going to navigate back to the directory I've been working from, my new rasters folder. And I'm going to call this V1 clip, just to remind myself that I've clipped that first kernel density. I'm going to clip it with a mask, and that mask is going to be the ranch boundary. I'm going to keep the resolution of 100 meters. One comment that I didn't note a moment ago, which is when you run kernel density, you as the user have to define the cell size. And in this experiment, we did it at 100 by 100 map units, or 100 by 100 meters. That's a decision that ultimately you have to make as a student as you work through whatever your own data sets are. But that is a user-defined decision. One rule of thumb is that if you intend to compare two different kernel density analyses, for instance, you want to map low birth weights and infant mortality as an example, if you wanted to map those two different data sets and compare them, you'd want to keep the cell size the same for both. Okay, so I've just performed the clip, and if I turn off my ranch, or if I bring the boundary to the bottom, we can see that I've now clipped my analysis to only the extent of my sampling. And if I wanted to, we could also change color. So to do that, I've double-clicked on Traps KDE to open the layer properties. Under render type, I've selected pseudo color, and here I can select a color ramp that I feel is appropriate. So here I'll go from orange to red, and I'll classify and apply. So I've gone to single pseudo color, I've selected orange, I've asked it to classify. It's created 5 classes. I hit apply and OK. And now I can see my greatest concentration of biting flies was here in the east central part of the study area, with an additional set of concentrations up in this area, and very few biting flies at all, if any, collected here in the west. Okay. So kernel density estimation is used to take a discrete data set, like a point data set, and produce a continuous distribution to look at concentrations on the landscape. Remember, if you have any questions, you're always free to email us or to reach out to us through the e-learning site and ask any questions that you might have, and we'll see you online soon.